tonight, so feel free to ask me questions at any point in time. I assume that this crowd was probably a little bit more well-informed on the topics I'm going to be talking about than a typical public talk audience, and therefore I've raised the bar a little bit in terms of the technical aspects of the talk. So hopefully you'll enjoy that. But if I do talk about something that's that doesn't make sense to you, yeah, I'm going to be telling you about the hunt for other worlds and life in the universe. And if you take anything away from this talk, get up and leave right now. What I want you to take away from it is that we're living in a very, very special time in human history, where for the first time we have the scientific knowledge, the technical ability, and the technological advancements that we need to actually start to pursue the scientific search for life. We'll preface this talk by saying I'm not talking about little green men or intelligent life. We can have a discussion about that afterwards. I'm talking about the search for basically simple life, microorganisms, for example. So I'm not going to talk about setting. I'm happy to extemporaneously talk about that after this talk if you like. Okay, so I'm a professional astronomer, and as a professional astronomer, I spend an inordinate amount of time on airplanes. Take several trips a month. As people that care for me actually know very well because I'm a son here. Invariably, I'll be sitting on the plane and some friendly person might be sitting next to me. This actually happens less and less. It's a little depressing. I think it has to do with cell phones and computers. But oftentimes someone sitting next to me will be talkative. We'll try to strike up a conversation with me. And if I'm feeling cranky or if I have a lot of work to do, which is most of the time, a lot of work to do, not cranky, well, I will say I'm they'll ask me what I do for a living and all, and if I'm cranky and I don't really want to talk, I'll tell them I'm a physicist at that point. But if I am feeling, collegial and communicative, I'll tell them I'm an astronomer. And almost invariably, their eyes light up. They often tell me when I was a child, I wanted to be an astronomer, but math was too hard, which I find exceptionally disappointing because math isn't hard. It's just that we have a lot of really bad math teachers, unfortunately. No offense to you if you're a math teacher, but that's true. They're always very interested in what I do. And when I say I look for planets around other stars, and find planets around other stars, they find that very exciting. And invariably, at some point in the conversation, usually relatively early in the conversation, pretty much without fail, they will ask me one question. And you can guess what that question is. You've just been asked it. Are we alone? Is there life out there? And so they think because I'm an astronomer, I have some advanced knowledge of this, or I'm authority on this or something. I don't know the answer to this question any more than you do. Actually, amazingly enough, you all seem to know the answer to this question, at which point I should probably just sit down and, because you've answered the question for me, it's good enough. But what I say is, as a scientist, I have to admit that I don't know the answer to this question. Okay? There's no definitive proof, as far as I'm concerned, that there is or is not life outside the solar system. Or even inside the solar system. But what I can say, and I think this is really the point, is that we're now at the stage where we can actually go and use scientific methods to try to search for life. And so I usually answer by saying, as a scientist, I have to say, I don't know. And that almost never satisfies them. They're like, yeah, scientist. Well, what do you really think? And I say, well, I don't know, but I'm trying to find out. And that's what I'm going to talk to you about, is how I and a lot of other people are going about the scientific process of trying to answer this question. So this is a very difficult question. It's been around for hundreds of years, and for a long time it was the province of philosophers and late-night barroom discussions, dorm room discussions, depending on which audience I'm talking to. And that was it. It was just a matter of speculation. But now we're actually embarking on the process of trying to answer this using scientific methods. Okay, so previous to roughly 1995. At least that's what I tell my undergraduates. It turns out it's not true, but if you want to know why, I will explain afterwards. You can ask me a question. This was the planetary systems that we knew of outside the solar system, i.e. none. Right? We knew of one planetary system, and that's of course our own. And so back in the day, before 1995, we really had no idea whether or not there were planets out there, or let alone whether or not there was life. So the way scientists have decided to break down this question is, instead of trying to answer that big question right off the bat, you can always try to skip to the end using SETI. It's kind of like going to the end of the book and finding out what happens. But sometimes it's a high-risk, high-reward endeavor. And what I work on, and a lot of other people work on, is trying to answer this question in a systematic fashion. So the first thing we ask is, are there planets around other stars at all? And so it's, again, a matter of speculation. It was unknown for a long time. Then once we determine whether or not there are planets, and of course we now know there are, we ask, do any of those planetary systems look like our own? By which I mean they have basically small glorified balls of rock in the inner part of the solar system, and then gas and ice giants in the outer part of the solar system. And then if we can answer that question, then the other question we want to ask is, do any of those planets look like Earth? By which I mean are rocky bodies with thin atmospheres located at the right distance from their host stars that they can have liquid water on their surface. And liquid water is important because we know that all life on Earth requires liquid water. And that doesn't mean that all life necessarily requires liquid water, but life as we know it requires liquid water. So the first step in searching for life is to search for what we know. So we search for life that rely on liquid water. And then if we find those kinds of planets, then we try to study them in detail and ultimately see if they have life. Okay? So that's the process. And what's amazing is when I started graduate school, we had answers to none of these questions, and now we are actually basically 3/4 of the way through this 4-step process. Okay? So I'm going to tell you a little bit about how I and my graduate students and postdocs are going about the search for to answer their first question, are there planets around other stars? So as I said, before 1995, this was the one planetary system we knew of. I removed Pluto here, a little revisionist history. And if I asked you to design your own planetary system, this might not be what you would come up with. It's a little strange if you think about it. Right? So the smallest planets are located very close in a very compact configuration close to the sun. The largest planet is sitting smack dab in the middle. It's made of mostly hydrogen and helium. These are made mostly of rocks, silicon, magnesium, and oxygen, and iron. Saturn is also mostly hydrogen and helium, and then Uranus and Neptune are somewhere in between. They have ice and rock, but they have about 20% of their masses in an atmosphere. So that's the solar system, and it's got this very unique architecture. If I had you design your own solar system, you might have them very egalitarian, have them all have the same mass and size, or very orderly, have the biggest one the closest, and have them go decrease in size, but that's not what a solar system looks like. But we had hundreds of years of imagining what other solar systems might look like, and naturally, because we're exceptionally closed-minded and not very imaginative, we thought all solar systems should be like ours. So it was an amazing shock to the field, and this happened just about a few months after I started graduate school, when we discovered the first planet. Well, again, this is what we tell our undergraduates, that it's not actually true. The first planet orbiting a sun-like star. So this was an otherwise unremarkable star, 51 Pegasi. So it's a star very much like the sun, located in the constellation Pegasus, right there. And it's a star that no one cared about, except for maybe its mother. So a Swiss team, the ARM payload, started monitoring this with a radial velocity technique, and they discovered that the star was moving back and forth along the line of sight at a very relatively high speed in a relatively short period of a few days. And from that, they were able to infer that that star was orbited by a planet about half the mass of Jupiter, but located only about with a period of only about 5 days. So its year is about 5 days. Well inside the orbit of Mercury if it were in our solar system. So this was a complete shock, because obviously the giant planets in our solar system would be somewhere out here, right? And instead, this giant planet was located right here. And how it got there, we don't think it formed there. We think that's impossible. But how it got there is the subject of many, many, many papers. We still don't know how these giant planets get so close to their host stars. So this turned the astronomy community up on its ear. Many people for a long time didn't think it was really a planet. So ingrained in their theories of planet formation that explained our solar system, they said it's impossible for this planet to be there. But we have now discovered many hundreds of such planets, and we know that they do indeed exist and are indeed planets, and basically made mostly of hydrogen and helium, just like our own Jupiter. Okay? So in the intervening 25-ish years, we have now discovered thousands of planets. So this is the cumulative number of planets as a function of time. The notable discoveries are noted here. You notice this is 51 Peg. The number of planets we knew before that is not 0. So that's part of why we lied to our undergraduate students and say this is the first planet outside the solar system we found. But then, as you go up, you see more and more planets. It's basically Moore's law, right? So, it doubles every 3 years or so, the number of planets that we know about. And of course, there's this big jump due to Kepler, which we'll talk a little bit more about later. So we now know that, yes, indeed, there are lots of planets around stars. So our solar system is not unique in the sense of having planets. It's unique in other ways, which I'll talk about. So that answers that question. And we're still looking for planets. So I'm going to tell you a little bit about some of my work about looking for planets. So I'm a tenured professor, which means when I say I'm looking for planets or I'm doing anything, I'm not actually doing anything. It's my graduate students and my postdocs that are doing all the work. I just take the credit for it. So these are a collection of some of my previous and current graduate students and postdocs. I really like this figure because you can actually see the personalities of each of the people from these. As you might imagine, this guy was a lot of work. But is very successful and a very good astronomer. This guy, he comes from Greenwich, Connecticut. You can just basically see, right? Also a very good astronomer. Thomas, I'm going to tell you a little bit of work about Thomas, a little bit about Thomas being when he was a graduate student. He's now a postdoc in Arizona. And so he was involved in, again, looking for planets surrounded nearby stars. He was involved in a search for planets using the transit technique. And what he used was to do this, so transit technique is just when a planet passes in front of the star, casts a shadow on the star, so you see that the star gets slightly dimmer for a few hours, roughly once every 3 days, because we're looking for these hot Jupiters, these Jupiter-sized planets located at a few day periods away from their parent stars. So you have to monitor, but the probability of alignment is relatively low, and the fraction of time it spends in front of its star is relatively low. So you need to look at a lot of stars a long time in order to be able to detect planets in this way. So the KELP Ground-Based Transit Survey, which I'm one of the co-PIs on, the other co-PIs are in Vanderbilt and Lehigh University. That stands for the Kilodegree Extremely Little Telescope. So you might imagine that this is not a very big telescope. In fact, it's not a telescope at all. It's a high-end camera lens, as you can see right here, stuck to the back of the CCD camera, and then it's put on in a robotic mount. And the whole thing is roboticized. It's in a telescope farm in southern Arizona. So every clear night, the telescope farm owner rolls off the roof. It's in a roll-off kind of roof shed thing. KELP wakes up, automatically takes images of the sky all night, over and over and over again, of hundreds of thousands of stars, and then once the sun comes up, it goes to sleep, and then it repeats the cycles over and over again whenever it's clear. And so KELP by now has monitored many millions of stars for up to a dozen years. Again, it's looking for planets that have this very favorable alignment relative to us, that it's edge on such that the planet passes in front, and so you get this little dip in brightness when that happens. So it's these little dips that we're looking for. Now, unfortunately, it turns out that stars vary for all sorts of reasons, many of which have nothing to do with planets, so it's kind of like trying to find a needle in a haystack. except you know, your haystack is actually made out of needles, so it's very, very difficult. But we have managed to find planets. So Thomas was actually sort of depressed for a long time because he was working on this for a year and a half for his thesis and hadn't found any planets. And so he actually took out an account in the OkCupid that was the Kelt survey, and said, you know, he was looking for planets. And then he made another OkCupid account of a planet that was looking for someone to talk to. And actually, people actually started trying to converse with these profiles. At that point, I started to wonder if he was losing his mind. But anyway, eventually we broke through and we found some planets. And this is Thomas having a very premature midlife crisis once we found some planets and buying a Mustang. And you can see his vanity license plate. This is the name of the star around which he found a planet. Can't blame him for that. But I'm not actually going to talk about this planet. It's interesting, but I'm not going to talk about it. I'm going to talk about the first planet that Thomas found. And that has the very unsexy name Kelt 1b. So we don't get to name our planets like after ourselves. I often have people like I'm planning when I'm having conversations with them, like I was talking about before. They're like, "Oh, if you find a planet, will you name it after me?" I'm like, I think my parents might come first. Just saying. You know, I just met you. So anyway, we don't get to name them. This one's called Kelt 1b. And Kelt 1, as strange as 51 Peg b is, this half Jupiter mass planet located only a few days away from its parent star, this object is even more bizarre. Okay. So Kelt 1b is orbiting a star slightly hotter and slightly more massive than the Sun, but it is orbiting its star at a period of 27 hours. Okay, so its year is just slightly longer than our day. Not only that, this planet has a mass that's almost 30 times the mass of Jupiter, but it has a radius that's almost that of Jupiter. So it's the super dense planet, or maybe we would call it brown dwarf. We argue back and forth about what to call it. Okay, a brown dwarf is just a failed star. And so it is so massive and so close to its parent star that it has managed to tidally spin up the planet, its host star, and then reorient it such that they are locked in each other's gaze as they orbit around in a double synchronous state. Okay? So this romantic situation, where they're looking at each other all the time, is not going to last very long. It's in about 2 billion years. The host star is going to evolve, run out of hydrogen, swell, and then unceremoniously eat its planet, which should result in a very spectacular transient event. So this is a very interesting system. I could talk a lot more about it, but anyway, we made it into the New York Times. They interviewed Thomas Beatty. At no point was my name mentioned. So I had to come into his office and I said, Thomas, you know, there were other people working with you on this. He's like, yeah, I know, I kind of forgot to mention it. So in this case, he actually took it, which is perfectly appropriate because he did most of it. So there he is. But the other, we've discovered about 23 planets now. We just announced our most recent one about 2 weeks ago. But the most interesting planet we found is, again, has a very unsexy name. It's called Kelt 9b, formerly the 9th planet that we discovered. This is a planet orbiting what's called an A star. So stars have names or letters designated to them: O, B, A, F, G, K, M, L, T. We live around a G2 star. This is an A0 star, which means it's much, much hotter. It's about 10,000 degrees Kelvin. So almost twice as hot as the Sun. It's almost 2.5 times larger than the Sun, and it's rotating at a period of less than of order a day. So as you look and see, squint in this artist's representation, the star is actually flattened, okay, because it's rotating so fast, just like Saturn. The bulge is out in the middle. Kelt 9b is orbiting at a period of only 1.5 days, so just a few stellar radii from its host star. It's roughly a Jupiter-sized and Jupiter mass object, slightly larger and slightly more massive. And it's orbiting at a polar orbit. So if the star goes like this, the planet's going around like this. Right? Very strange orbit. And because the star is so massive and so hot, it emits an enormous amount of radiation, much more radiation than the sun, and in particular a lot more high energy radiation, ultraviolet radiation. That has the effect, and this planet is tidally locked, so it's only seeing, it has a day side and a night side, just like the moon. So it's only seeing, half of it is seeing the star, and that part is being blasted by this enormous amount of radiation. And that makes Kelt 9b, the planet, actually only just a little bit cooler than the sun. This planet is, if it was in isolation, would be hotter than most stars that we know about. Okay, so it's a very unusual planet. It's so hot that there are no molecules in the day side of the planet, and the only constituents in the atmosphere are metals. And in fact, very recently, iron was discovered in the atmosphere of this planet, so it has an iron sky. It's quite amazing. And this is roughly the colors if you would go see the system. Look like, and it's almost to scale. This is actually to scale, so you can see the planet, the star orbiting this way. And not only is this planet so hot that it's hotter than most stars and all the molecules are disassociated, but it's also evaporating at a very large rate. And it's unclear whether or not it's going to survive for the rest of the lifetime of the star, or if it's going to be completely evaporated by the star over that time. So this is a very interesting and unusual system. We got published in Nature, yay, my first Nature paper. I think it's just because Nature fits so well right here. I can tell you that was not an accident when I asked the artist to design this picture. And that's great. But what's even better is that Chris Evans, yes, the Chris Evans, Captain America, tweeted about this discovery. He said that a host star is more than twice as large and nearly twice as hot as the sun. Is there anything cooler than space? Real life has. So once you've been tweeted about by Chris Evans, you can basically recover. So that was pretty exciting. Okay, so we've answered the question, yes, there are planets orbiting other stars, and part of my team is help to contribute to that. But the next question we want to ask is, are most of those, what fraction of those planetary systems look like our own solar system, which, like I said, is an unusual architecture. So in order to do that, we have to use a different method. We can't use the transit method because it's only basically sensitive to very close planets, because they have to be close enough that they have a good chance of being aligned such that they pass in front of their parent stars. So instead, we use a technique called gravitational microlensing, which was actually first thought of by Albert Einstein, who famously predicted it would never be observed. It was one of the few cases that Einstein was wrong. We've now observed about 10,000 microlensing events. And my former advisor, Andy Gould, actually was one of the people that invented the idea of using microlensing to find planets. And the technique works, it's pretty simple. If you stare at a star long enough, in this case we're talking about stars in the center of the galaxy, in our galactic bulge, long enough being about 500,000 years, eventually another star somewhere between you and that more distant star is going to pass close enough that its gravity will take that star's light and actually split it into two images. And then those two images will then come to the observatory. So I actually find it quite amusing to think that if there are stars up in the sky that actually have double two images of them. Unfortunately, those images are too close together for us to see resolved. But what we do see is the background stars get magnified because some of the light that would have gone in other directions gets pulled into our direction. As the foreground star comes into alignment and moves away, the background star gets brighter and then it gets fainter. Now, if this foreground star happens to have a planet, and that planet happens to be located near one of the paths of these two images, then that planet has gravity and it will do the same thing, and you'll get a momentary brightness, brightening of that background star. And because these images pass at distances that are roughly the distance of Jupiter from the Sun, that means we're sensitive to Jupiter-like planets and even more distant planets as well. And this sounds kind of like science fiction, but just to show you that it's real, this is an actual image of the center of our galaxy, and you can see this star that starts out very, very dim, and then over time it gets brighter, and then suddenly it jumps in brightness when the planet becomes aligned with one of the images, and boom, that's the detection of the planet. So this is the first planet discovered by the gravitational microlensing method. And we've now discovered about 40 planets using this So one of them was actually quite interesting. So this is when I was a postdoc at Harvard. So this is just the brightness of the star as a function of time. And these brightening events last typically a few weeks. So I was like I said, postdoc at Harvard, and I was working on trying to monitor this star, which we knew was being microlensed because we could see it get brighter. And we saw this little interesting extra bump up here. So we thought something interesting might be going on. And then as we watched, it started getting brighter and brighter and brighter, which meant that the alignment of the foreground star with the background star was going to be very precise, which makes it very sensitive to planets. And so as we were watching it, it was about 11 o'clock at night, and data from halfway across the world came to my desk, my computer, and showed that. And it's a little hard to see, but what actually happened is the star suddenly jumped up in brightness over the course of the night and then started to die. And you could just barely see the initial descent. And then at that point I knew that this had to be a planet, so I modeled the event using my computer and discovered that this was caused by a Saturn Mask planet. So I was super excited. I sent emails out to all of my collaborators that are trying to observe this and said, you know, we have to keep observing the star because we just found a planet. And then I predicted, based on my model, what the future of that brightening of the star would look like. I predicted that it would drop very precipitously. It would keep dropping and be very low brightness. It would have a brief re-brightening and then drop again and then finally fade back to its normal brightness. So around 1 or 1:30 at night, you know, I had sent out this email. I was very proud of myself, very excited, and so I went back to my apartment in Boston, in Cambridge. Took about a 4-hour nap because I was waiting for the new data to come in to prove my model. And the new data came in, and I was saying, okay, it's going to be right here, and instead, it was all the way up here. So I was like super depressed. I was like, you know, maybe I should seek another career. I was thinking what I'm doing, you know, what's going on. And you know, meanwhile, we kept watching the event, and after that, it did exactly what I predicted it was going to do. Okay, so I was totally dumbfounded for years, about a year and a half. I couldn't figure out what the heck was going on with this event. Until finally I realized that actually my initial model was totally fine. There was a Saturn Mask planet in this. It just was incomplete. There's not just one planet in the system, there's two. Okay? And the second planet is what caused this extra brightening, which my original model didn't account for. Always keep your mind open. And I finally figured it out, and it turns out that the first planet I found has a mass of roughly Saturn and is located roughly half the distance from its parent star that Saturn is located from the Sun. The planet that created that extra deviation that I did not expect is roughly the mass of Jupiter and is located roughly half the distance of Jupiter from the Sun around its parent star. And the parent star is about half the mass of the Sun. So it's basically a 1/2 scale model of the Jupiter, Saturn, and Sun system. So we thought that was close enough to call it a solar system analog, published it in Science, you know, called up the New York Times, made it to front page, below the fold, that's okay, still the front page of the New York Times, and it was super exciting. So it was the first evidence of that there are, in fact, solar systems like ours, at least solar systems that have two gas giant planets in roughly the same configuration and mass as our Jupiter and Saturn. So that shows that at least some planetary systems, yes, do indeed probably look like ours. And, you know, we're brave, foolish maybe, but anyway, take one system, and you can estimate the frequency of solar system-like systems, and we found out that roughly 17% of all systems look like have these Jupiter-Saturn analogs. And that has a very, very large uncertainty associated with it because we just have one detection. We've had more sense, but the error bars are still large. But it means that, and the result is held up, solar systems like ours are neither exceptionally rare, but they are not the majority. So this is actually quite interesting. It's one of the first times the Copernican principle has failed, which is the Copernican principle, of course, is that we're not special. We're not unique in any special way. We're not the center of the universe, the center of our galaxy, the center of our solar system. We're just an average, we're in an average location around an average galaxy orbiting out in the suburbs. But in fact, our solar system is actually in the minority of what planetary systems are. Okay, so that's very important. Okay, so we've answered this question. Yes, there are planets around other stars. We've basically answered this question. Yes, there are solar systems that look like ours. What about answering the question, are there rocky planets at the right distance from their parent stars to have liquid water if they have an atmosphere? Right? That question took the NASA's Kepler Space Telescope, which I'm sure you've all heard about. So Kepler stared at one patch of the sky, roughly 100 square degrees, for about almost 4 years before its reaction wheel failed, and then it had to do something else, and then finally it died. It ran into a funeral. Very sad. It sounds almost sad. Anyway, so it looked at this patch of sky for almost 4 years and stared at about 100,000 stars to look for a periodic dimming of sun-like stars. But if you want to detect the Earth passing in front of the sun, first, the probability of that happening, of having the right alignment, is only 0.5%. The dip itself is only 1 part in 10,000, right? Because the Earth is about 100 times smaller than the sun. And it only lasts for about 10 hours out of a year. So you have to look at hundreds of thousands of stars at a precision of better than 1 part in 10 to the 4, it's closer to 1 part in 10 to the 5 is what Kepler achieved, continuously to find that 10-hour eclipse that lasts about 0.1% of the period, has a depth of about 10 to the minus 4, right, and only has a probability of happening of about 0.5%. Even that's if every star has an Earth, which doesn't. But that's what it sounds impossible, sounds really crazy. Astronomers do lots of crazy things, so we built this telescope to do that, and that's exactly what we did. The first thing Kepler found was that small planets are exceptionally common, much more common than giant planets. And in fact, Kepler found that planets with sizes between that of the Earth and that of Neptune are actually the most common planets that Kepler found. There are no analogs to these planets in our solar system. It was completely unexpected that there would be planets like this. We don't even know what to call them. Some people call them super Earths. Some people call them mini Neptunes. We don't really know what to call them because there's nothing like it in our solar system. And they turn out to be the most common planet that Kepler's found. But Kepler was sensitive to Earth-like planets orbiting sun-like stars barely. Unfortunately, if the reaction wheel would have failed, it would have had much more sensitivity, but it did have some. And the estimates are that about 1 in 4 sun-like stars hosts a rocky Earth-sized planet at the right distance from its parent star to have liquid water, if it has an atmosphere, which you don't know, because all we're seeing is the solid part of the planet passing in front of the star. So we have to go and look and see if those kinds of planets actually have Earth-like atmospheres. Okay. Now, what we can actually improve this estimate using the next telescope. So NASA always has a large flagship mission, they call them, that's waiting in the wings for after the next one dies. Sometimes it has several, so I was lucky enough to be part of the golden age of astronomy when we had Spitzer, the Hubble Space Telescope, Kepler, Chandra, lots of space telescopes. Unfortunately, Kepler is now no more. Chandra and Hubble are keep going, but eventually Hubble is not going to last forever. And the next and then we're going to launch JWST soon. That'll be the next large flagship mission, which will be very impressive. Unfortunately, I don't have time to talk about that. And what I've been spending roughly about 10 years of my life on was the mission that was picked to follow on after JWST, which is called the Wide Field Infrared Survey Telescope. And this is a telescope that's roughly the size of Hubble, but it has a field of view that's about 100 times larger than the field of view of Hubble. So it's like it has a wide-angle lens, and that means it can map the sky at roughly 100 times the pace of Hubble. And that's nice because remember I said with the microlensing method, you have to stare at one star for about 500,000 years to get this alignment. Well, no one's that patient, and it's longer than the graduate student lifetime. So typically what we do is we look at, instead of one star for 500,000 years, we look at hundreds of millions of stars for about a year, and then we find tens of thousands of microlensing points, and that's what WFIRST is going to do. And just to show you how powerful WFIRST is going to be, this is a canonical plot that every exoplanet talk will show. It's mass on this axis, spanning about 6/4 of magnitude, and separation from its parent star on this axis, spanning about 4 orders of magnitude. And these are all those planets that Kepler found that have no analogs to the planets in our solar system. Kepler's found about 4,000 planets right here. But you can see that Kepler's sensitivity is limited to short periods, as I mentioned, because you have to have this right alignment. And you have to detect more than one transit, which means that if the period is more than about 4 years, you're not going to see, you wouldn't have seen it with Kepler. So there's this vast region of parameter space out here where Kepler was completely insensitive. In fact, if every single solar system looked like ours, Kepler would have found no planets. Right? Think about that. Right? It found 4,000 planets. Right? That tells you how unusual our solar system is. W first, its sensitivity is using the microlensing method can be shown here in this blue line. This plot was made by my postdoc, Matthew Penny, so I call it the Penny plot, which has made him somewhat famous. You can see that, and so these are his estimates of the sensitivity that W first would have. These are a realization of the planets that W first might find. Don't believe it, it's all made up. If we knew that, we wouldn't be bothering to do this. But what you can see is the planets in our solar system are also plotted on here. And W first would be sensitive to analogs of all of the planets in our solar system, except for Mercury right here, but who cares about Mercury? And then you might notice there's 3 other dots there. Anyone want to guess what those are?
Ganymede.
Yes.
Tight.
Yes. So, W first would be sensitive to even large moons, even if they were just orbiting their star by themselves, or if they're orbiting other planets as well. So it would fill out this whole region of parameter space, and because planets have mass and they have gravity, that means that they can bend light just like stars do, and so they can create their own microlensing bends. They don't need a star to do it. And we think that free-floating planets are probably very common in the galaxy. Think about that. There are probably planets just floating out there on their own, looking for a star, all lonely. Got rejected by their star. And W first will be able to measure the frequency of those kinds of planets with masses all the way down to roughly the mass of Mars. Right? So we'll see how common those really are. And it will detect a lot of planets. Matthew's current estimate is about 1,400 planets. You may have seen an article in the Columbus Dispatch about Matthew's recent paper predicting this particular. Okay, so Kepler and W first will tell us all about planetary systems, tell us about the frequency of rocky planets orbiting sun-like stars. So just in the last 25 years, we've actually answered 3 out of the 4 of these questions. But what about this last one? Well, this last one is the big one. That's the one we really want the answer to. It's what drives me as an astronomer. Is there life out there? I want to know the answer. I want to be able to turn to that person on the plane and say, yea, verily, we've detected it, or we've looked and looked and looked, and we can't find it. So how do we do that? It would be great if we could get an image like this of another planet. That's never going to happen. Never. It's not going to be. You're not going to see it. I'm not going to see it. Your grandchildren aren't going to see it. It's not going to happen. You may even be happy with this, right? Some pixelated version with just a few resolution elements across. That's also not going to happen for a very, very long time. The best we can actually hope for in our lifetimes is that. Everyone know this picture?
Pale blue dot.
Pale blue dot. All right. And where did it come from?
Voyager.
And who ordered Voyager team to turn the telescope around and point it back at the sun? Even though they really didn't want to, because they were afraid it was going to hurt it.
Carl Sagan.
Carl Sagan, yes. So he convinced them, after much arguing, to turn Voyager around, look back at the sun, and there is Earth. It is unresolved. This is a photograph, but if this were a digital image, we would say that this is contained in less than a pixel. So it's unresolved. And you can see this little streak of light. This is just due to bad optics in the Voyager camera, but it is actually prescient for reasons I'll tell you. So this is the best we can hope for: an unresolved to detect an unresolved pale blue dot. Okay. And you might think that would be pointless, but actually. It's not. But even detecting that pale blue dot is hard. So the analogy is that everyone uses is that it's like trying to detect, because the pale blue dot is sitting right next to a star, right? And if it's at a distance, even the nearest stars are distances of something like 30 light years. If you want a large enough sample, you have to go out to roughly 30 light years. So you have this very faint planet sitting next to a very bright star. In fact, the planet is 10 billion times fainter than that star. Okay? And so that means that for every single photon you get from that planet, you have to get rid of 10 billion photons from that star. And if you miss just one, then you'll confuse it with the planet. All right? So this sounds crazy. And the analogy is, it's like trying to detect a firefly roughly 5 feet from one of those industrial searchlights that they have at Hollywood premieres. When the firefly and the searchlight are sitting in Los Angeles, and you are standing in New York City. That is roughly the scale of this problem. Right? That sounds hard. Sounds crazy. Why would anyone work on it? I told you astronomers are crazy. But actually, it turns out, I went and looked up the luminosity of a firefly. Not easy. Did it, found out how luminous the firefly was. I went and I dug through the industrial owner's manuals of searchlights, found out how luminous they were, because I wanted to know, is a firefly really 10 billion times fainter than a searchlight? The answer is no. It's actually about 1,000 times brighter compared to the searchlight than the Earth is compared to the sun. So this problem is actually 1,000 times harder than even that analogy, which sounds already crazy. It is, okay? And yet, I've been spending the last 3 years of my life trying to decide to design a mission that would do this. So, you know, be careful. Don't let me run to sit I have been, come on. All right, so how do we do that? Okay, so we have to block out that light from that star, but still retain the photons from the planet. Really hard. And again, you have to be perfect to 1 part in 10 billion, otherwise you're going to screw it up. So one of the ways we do this is called a coronagraph. It was originally designed to block out the light from the sun, so you can see the sun's corona like a solar eclipse, right? But now this same technology is used to actually block out the light from the star, but keep the light from the planet. And the idea is relatively simple. Right? You have light coming in from your telescope. All you do is you take that light and you take the light from the star, you move it out to the outskirts, and then you put a ring there and blocks it. Since the light from the planet comes in at a different angle, that means that that light from the planet won't be blocked. Right? Sounds easy, right? Except every tiny little imperfection in your telescope, in your mirror, anything, right? If it scatters just 1 photon out of that 10 billion, you're screwed, right? So you have to make your wavefront of your light perfect, right? And we can't make perfect optics. So what we do is we take a mirror and we have it correct that wavefront, right? And give you very clean wavefronts. And as a result, you end up being able to detect planets that way. So that's one way to do it. The other way to do it is, in my opinion, even cooler. It's called a star shade. The idea is that you use techniques of origami to roll up something that's basically the size of a baseball field, and it unfurls by itself, and then you fly it about 100,000 kilometers away from your telescope, and basically it's like putting your thumb over that star, except the thumb is 52 meters in diameter, and you have to, the edges have to be manufactured to about 1 micron. It has to unfurl to a precision of about 1 millimeter, and you have to align it with your telescope to about a few feet. And it's 100,000 kilometers away. So easy. But if you do that, then the light from the star never actually makes it in your telescope, but the light from the planet does because it's not being blocked. So you can you can detect the Kepler dot relatively easy that way. JPL, which is like sort of my other home, is working very hard. All right, so now we have this pale blue dot using these techniques. What can we do with it? Well, we can take it, put it through a spectrograph, or in other words, a prism, break it up into its component wavelengths, and look for features that are where the light is being blocked from the planet and is being blocked by the atmosphere. Okay, and the things you can look for, right? One, you can look for a rise in the brightness towards the blue. This is what makes the sky blue, Rayleigh scattering. So that tells you got an atmosphere. You can look for signs of water vapor in the atmosphere, which is an indication that you might have a liquid ocean. You can look for oxygen Or you can look for carbon dioxide, which is a moderator of the temperature on the Earth. And then you can look for oxygen and ozone, all of which on the Earth is created by life. And you can try to look for methane, most of which is created by cows. So you can detect extrasolar cows. So you can actually, just with this pale blue dot and taking a spectrum, really powerfully probe the contents of the atmosphere of this planet and see not only if it's potentially habitable, but if it actually is inhabited with some form of life. That's amazing to me. So I've been working with NASA to try to develop a roadmap for the next few decades and what we're going to do. So here we are today with with Kepler. In the next decade, we're going to launch W first, which I've been working on. I've been involved in a study for the last 3 years, along with 20 or 30 of my best friends, trying to design a mission that would use a star shade and a chronograph to block out the light from the star and detect a pale blue dot, take its spectrum to see if it's potentially habitable or inhabited. And then we've even thought about the very distant future where you actually have a fleet of these telescopes all operating in conjunction, which would actually allow you to get that pixelated version of the Earth that I showed, and you could actually see if that Earth 2.0 has continents, oceans, clouds, measure its climate, etc. That's a long way away, right? This is kind of science fiction. This is not. That's what I really want to impress upon you. Everything I said makes it sound really, really hard, but there are some really, really smart people out there that have figured out how to block that light, take that spectrum, and we now have a viable mission design. It's really not that expensive. It's actually less expensive than the Hubble Space Telescope or the James Webb Space Telescope is, and it can actually do this. And it can be launched by 2030s, right? And we could actually go and look for life and potentially find signatures of life. So this mission is called the Habitable Exoplanet Observatory. I'm one of the chairs of the study, along with Sarah Seeger at MIT. And so here's the telescope with the chronograph. Here's a space daisy starshade. These are my friends in the science and technology definition team. And the reason why this is possible now, but was not possible 10 years ago or any time in the past, is that we know things now that we didn't know 10 years ago. One, we know from Kepler that small planets are very common, and that planets in the right distance from small planets, rocky planets, the right distance from the parent star are not rare. About 1 in 4 sun-like stars have one. So that means that we don't actually need a big telescope to get lots of photons. To do this, we can do it with a puny old, just 4-meter telescope, just twice as big as Hubble. But that's good. So that makes it less expensive. And so this is, I told you I was going to get into some little technical stuff here, so if that doesn't interest you, you can feel free to tune out. These are the properties of the telescope that we're talking about. And so it's only a 4-meter telescope. It's off-axis, which means that the second mirror of the telescope is offset, so it doesn't block the light from the star, which means it doesn't scatter the light from the star. That's good. It has a chronograph, as I said. It also has the star shade. It has some other cameras to do other exciting astrophysics. It will hopefully be launched on an SLS Block 1B, so the SLS is the space launch system that NASA is working on. That would be for the telescope. The Starship would need a separate launch vehicle, but one that we already have available or will soon with the Falcon Heavy. It will be at L2, that's where JWST will be, so that's the Lagrange point, that's the stable point behind the Earth. Relative to the sun, it's where the sun and Earth's gravitational potential cancel out. So it's a very quiet place, which is good. And the idea is to launch this sometime in the mid-2030s if, in the last 5 years, if the powers that be decide that this is what we want to do. So every 10 years, astronomers get together, they decide what they want to do for the next 10 years, they usually prioritize at least one large space-based mission, and we're hoping that this is the one that they launch. So we're writing this report now. I should be writing this report right now, not talking to you. That we will submit to the Decadal Survey, which has just started. I'm also supposed to be writing white papers that are input to the Decadal Survey now, instead of on green. That's what it's tonight. Anyway, we hope that it will be launched. They'll pick it, and it could be launched sometime in the mid-2030s. And if you think about it, that seems like a long time away, but at the same time, it means that within that time frame, we could potentially actually answer this question: is there life on other planets? Like, that's an amazing thing. Imagine until 2036, some announcer comes on the television and says, I have news for you. The Sagan Space Telescope, which is of course what this is going to be called, has discovered life on another planet. I mean, wouldn't that be amazing? Or maybe not. Maybe we'll go and look at all the planets and there won't be life. And we'll find out that, to the best of our knowledge, we're alone. That would also be very profound. But the point is that we will know this. So this is also a little geeky stuff. This is the technology demonstrations that you have to do to make sure that this works. NASA does not like to take risks. It is very, very risk averse. So you have to make sure these things work. Have to. And that tends to make missions more expensive, but it also means we're not wasting your taxpayer money by launching things and having them not work. So this is actually a JPL, Jet Propulsion Lab, a tech demonstration of a half-scale starship map with just a few pedals, just to show that you can unfurl it and manufacture it to the right tolerance. So we're not going to get an image like this. We could get an image like this, but it's not going to be in our lifetimes. This is an image we could get in our lifetimes of a planet around another sun-like star in the habitable zone. And with that image, we could take a spectrum. We could determine whether or not that pale blue dot is habitable, and maybe even determine if it's inhabited, at least by simple life. This is an example of the kind of spectrum you get. It's kind of noisy, but hey, this is 1 factor in 10 billion, and it's an Earth-like planet. So, you know, that would be amazing. If I live to see this, I will die a very happy man. And hopefully be famous. And the habitable X we're going to do will also be able to take spectra of all the other planets in the system, so we could put that planet in context and see if the solar system are like ours. Here are some of our favorite targets. You know a lot of these by name. The really exciting part about a lot of this is that we already know that the half of these are inhabited because Star Trek told us. So that's good, right? So I just want to leave you with this idea that we are in this very special time in human history. For the first time, if we so choose, we have the technology, the resources, and the knowledge to be able to build something that can go and ask this question and scientifically try to answer this question: is there life on other planets? Thanks. Mike Brown doesn't search for planets outside our solar system. He looks for planets inside our solar system. And mostly he looks for not things that are not planets, but we call them dwarf planets. So he found a planet called Eris, which turns out to be roughly the size of Pluto. For a while we thought it was bigger than Pluto. And that's the reason why Pluto got demoted. I told you that we lie to our undergraduate students and say that 5110 was the first planet to be discovered around another star. That's not true. Before that, there were planets discovered around a pulsar, a dead star, about 2 years before that. And actually, about 6 years before that, a planet was found around a star, but the author was just a little bit less, a little bit more cautious in calling it a planet, but is now considered a planet. And even before that, a pair of Canadians, Walker and Campbell, invented a technique by which you filter the starlight through a gas, and that imprints the lines of the gas. That allows you to measure the wavelength of the light very, very precisely, and you can see the spectral lines moving back and forth very, very well. Unfortunately, the gas they chose to use was hydrogen fluoride. Anyone that knows anything about hydrogen fluoride? It's a colorless, odorless gas that basically kills you on contact. So they had a little gas cell made of hydrogen fluoride, which they had to heat up because it has to be warm enough. And so there was always a worry that this gas cell would break and that they would die. So the lore is that one of the Campbell and Walker, they would take turns, would be standing outside of the observatory room where there was a window, watching the person that was actually taking the observation, holding 2 gas masks in his hand, so that in case something happened and the gas cell broke, he could run in and save his partner. I don't know if that's true or not. It's a good story.
Why wouldn't you just wear the gas mask?
What?
To check it.
I think the story is almost certainly possible.
Just curious what your first motivation was to go in this direction, where your interest first originated, how you followed that through schooling?
So, it's a good question. When I was in second grade, my second grade teacher, Mrs. Eleanor Gregory, and I was living in a very small town, about 4,000 people, a old coal mining town in south central Illinois called Staunton, about an hour away from St. Louis. Very rural, football was king. I was not into football. But she was a very good teacher, and she gave us an assignment to go home and look up and memorize the name of the 9 planets, back when there were 9, in order from the distance of the sun, and come back and then recite the names of those planets. So I went home. My parents had gotten a subscription to National Geographic, and with it came 3 picture book atlases, or picture atlas books. One of them was called Our Country, and talked about all of the 50 states. One was called Our World, and it talked about all the countries at the time, many of which no longer exist. And the other one was called Our Universe. And so I plucked the All Our Universe book off the shelf, and I started reading it, and I read it cover to cover, and I not only memorized all the names of the planets, but there was one section that imagined what alien life on the solar system might look like. So it imagined blimp-like creatures floating in the atmosphere of Jupiter. It imagined beings living off of pure hydrocarbon skating on the surface of Europa. It imagined pouchers, they were called, that lived in Venus, but they couldn't stand, and they had to always hold one foot up because it was so hot. It was all ridiculous, but I was so fascinated. I was hooked. And so I walked up to my parents and said, "I'm going to be an astronomer." And they're like, "Yes, yes, yes, yes." They figured that, the next day I'd say, "I'm going to be a fireman." But no, I just kept saying I'm going to be an astronomer. And after about 10 years, they started believing me that I actually did want to be an astronomer. So that's what I was. And then I went to a school for gifted students called the Illinois Math and Science Academy. It's a boarding high school. It's about 3 hours away near the suburbs of Chicago, and we've had some awesome teachers there that continue to kindle my interest. Went to Michigan State University, not Michigan State, and got my degree in astrophysics. I registered as an astrophysics major from day one. Got my BS in astrophysics, got accepted to graduate school at Ohio State University, got my master's PhD, went and helped develop this method of micro-lensing searches for planets, went to the Institute for Advanced Study where Einstein finished out his career, started working on transiting planets, and then went to Harvard for 3 years. These were sort of postdocs, or you would think of them the equivalent of residencies for doctors. And then I was lucky enough that Ohio State hired me back after getting my PhD there, and I've been there since 2006. And somewhere around 2004, discovered my first planet in collaboration, and now I've discovered over 50 planets or so.
You may not be a gambling man, but if you were, suppose you really need the money, what percentage chance would you assign it that by the time that you are astronomer retirement age, we've seen convincing evidence of an inhabited or has been inhabited planet?
I would give it a fairly high probability, and I'm not going to try to narrow that before assuming we make it through the next year.
Yeah.
It's a big if. Assuming we make it through the next year and sort of stop being so crazy, then I would say the probability is high that we will find tentative evidence for life on another planet, but not definitive.
More than 50?
What? More than 50%. So the reason why I say that is just because we know that life on Earth originated a very, very long time ago. In fact, evidence suggests, and this is controversial, but evidence suggests that as soon as life could have arisen and not have been blasted by all the debris of solar system formation and killed off in a global asteroid impact, right? As soon as that stopped happening, right, life seemed to have arisen, right? It took complex life much, much, much longer, which is why I'm much more skeptical about whether or not there's intelligent life. Also because I think intelligent life has this adolescent phase that we're going through right now, where we have a tendency to blow ourselves up or, destroy our planet or whatever. But simple cell life, I think there's lots of evidence that it probably is quite common. If we go to Mars and we dig under the soil and we actually find evidence of past life there, because we know Mars had a much bigger atmosphere and a lot of liquid water on its surface in the past. So it could have harbored life. In fact, we could all be Martians because we trade germs all back and forth between Mars all the time. So Mars could have, life could have arisen in Mars, or even Venus actually, before it went bad, and then thrown a rock to the Earth, and that's how life started. That's possible. But if we go to Mars and we see evidence of past life, then I think, and we're pretty sure that it arose independently of life on Earth, then I think that would be exceptionally strong evidence that life is very pervasive. It finds a way. And like many people have said, a lot of chances, right? 4.5 billion years is a really long time.
I wanted to ask, why were you concerned about the other solar systems like ours? In other words, I get the idea of finding planets that are about the same distance from their sun as ours is, but why do you care if there's other solar systems that have a Saturn and Jupiter-like planet and so on?
Well, I mean, I'm self-centered. You know, I like our solar system. I want to see if there's others out there like ours. But more seriously, there are lots of reasons why we might want to know, right? So we think Jupiter was the first planet formed in our solar system, and Jupiter is a big bully and likes to throw things around because it's so massive. That's both good and bad. So occasionally it throws asteroids towards us, and roughly any day now, an asteroid is going to hit us that's going to cause a mass extinction if we don't do something about it. And it happens once every 100 million years, and the last one was roughly 100 million years ago, give or take. But it also has this habit of actually preventing things from coming into the solar system. So what we think happened, so the origin of, so there's this paradox that in the protoplanetary disk where the Earth formed, temperatures, the pressure was basically zero, because it was basically, I mean, it was in a disk, but there was almost no pressure. Might as well be the vacuum of space. And as you probably all know, once you get below a certain pressure, you can't have liquid water. You're either gas or solid. And the temperature where the Earth formed was such that any water would have to have been in gaseous form, right? So it's this paradox that the place where you can have liquid water with an atmosphere, the habitable zone, almost certainly forms planets that are dry. And those planets therefore have to get bombarded by something that's wet. And so that could be either the asteroid belt or comets or something like that. And currently, I think most people favor the asteroids. So Jupiter actually was important for giving us the actually very small amount of water that we have on the Earth. Uranus is actually very water poor in many ways, but it has just enough water for life, which is a little worrisome in the other direction about whether or not that is coming. So that's one of the reasons why it's important to know whether or not there's planets outside where you could have water ice, so that it gets delivered to the Earth. And if we didn't have Jupiter, then all of those things would come into the Earth, then the Earth would be a Kevin Costner water world, right? Which also isn't good for life because you don't have the carbon dioxide cycle, which is what moderates life. So what we think water worlds are probably uninhabitable. We don't know that for sure.
As a JPL insider, when do you think the JWST will finally be there?
The $10,000, or the $8 billion. I think they're going to get it. I think they're going to. The launch date is going to slip one more time, but I think it's only going to slip by 5 months. So I think it's going to be 2020. It better be. Otherwise, basically Congress said, "Yeah, this is your last chance, guys. You got to get it right," because they had to put by law a cap of $8 million for the cost of JWST back way in the day when they were screwing things up really badly. And they said, "Okay, we're going to give you the money to do this, but if you go over 1 penny over $8 billion, we'll be cancel the mission." And then when it got delayed, it was obvious they were going to go over $8 billion. And so they said, you said that, can we please launch it now? We've already spent it. Just a little bit more. And Congress was like, okay, a little bit more, but that's it. No more. Last chance.
This might be more of a biologist question, but do scientists think that the basic structure of life on Earth, for example, DNA, is that likely to be the structure that we find elsewhere, or are there other possibilities of other dynamics that would bring about what we might recognize as life.
Yeah, so how would you define life? That's the first question that you're sort of asking. And we don't really have a good, I mean, astrobiologists have a definition that they use, which is self-sustaining organisms that undergo Darwinian evolution. Other people have definitions that it's systems that lower their own entropy. Because basically, what is it when you die? It's when you finally succumb to the second law of thermodynamics, and your entropy basically increases to the point where you're no longer able to function. But the reason why we look for life as we know it is because you have to start somewhere. And if I asked you, and I'm going to quote my department chair, who likes to say this, if I went and told you to go find me a dog, you would probably know what to do. If I went and told you to go find me a not dog, that might be a little bit harder. Right? So if I go and tell you to find life like the Earth, you know what to do. If I go and tell you to find life it's not like the Earth life, well, that's really hard. So, but there are good reasons to think that life might actually be very similar to life on Earth, right? So we're made up of, the two most important things we're made up of are carbon and water, right? And so water is made up of the two most common elements in the universe that actually play well with other elements. Right? So the three most common elements in the universe in order are hydrogen, helium, and oxygen. Helium does not bond. It's a noble gas. It's snooty like that. But hydrogen and oxygen love to bond with each other and make water. So water is abundant everywhere. And then the fourth most common element is carbon. And that's the basis of most of life. And carbon has lots of amazing properties, like it forms double bonds that allows you to make these polymer chains and things like that that are essential for organic chemistry, right? You might think silicon, right? It's one down on the periodic table. It should have similar properties. Because of that, it's in the same column, just one more row down. But actually, silicon doesn't form double bonds, so it can't make these very complex molecules. And the thing it likes to bond most with is oxygen to make silicon dioxide, which is also known as sand. Not good for life. Not good for life at all, right? What kind of solvent would you use other than water? Methane? Well, methane's only liquid at very relatively cold temperatures where chemical reactions that support life are very slow, and it's only liquid at a very relatively narrow range of temperatures. It's also more dense when it's solid, which means that if you had a methane ocean, the methane ice would sink if it froze, right, which would kill life that was swimming in it, right? One of the nice things about water is that it's less dense when it freezes, so that the ice keeps at the top, and you can still have nice fishies living in your ponds, or organisms, or whatever, below. So there's lots of really good things about carbon and water that make it not so surprising that that's what life in Earth came to utilize. That being said, who knows, right? Just for the same reasons of there's so many different possibilities out there, places where life could have originated, there's probably many different ways that you can have self-sustaining organisms that go through Darwinian evolution that maybe don't involve carbon and water or DNA. Yeah.
What makes a good math teacher?
I had a friend of mine who went back to school for nursing, and he had to take a class, had to take algebra to do it. And he had been told as a child that he had math dyslexia. Turns out there's no such thing, right? It doesn't exist. But he was convinced that there was no way he could do this because he was told he was terrible at math. So I sat with him for a month every night and went over his algebra homework every night. And it was like pounding my head against the wall because he was just convinced he couldn't do it. And then eventually the light bulb went on, bam, and from then on I didn't have to do anything anymore. Right? You just have to explain to people what the basic concepts are. If you try to just give them equations and say, manipulate these with algebra, without giving any context or any reason or anything, and just have it be a set of things that you're memorizing, you're never going to get people to do math. But if you actually explain to them the underpinnings of what math is, like what's an integral? The integral is just actually calculating the area under a curve. That's all it is, right? If you explain it in those terms that people are familiar with, right, then it's not hard. So calculus itself is actually not very hard if you explain it at a level that, or explain it in a way that actually people have some contact with in their own daily lives. So So that's what I think makes a good math and physics teacher and any kind of teacher is you have to make that connection to something that they understand and they experience. And you have to figure out how to do that. What are you tapping into that will allow them to grasp the underpinnings of what you're trying to do, not just what are the rules of what is the multiplication table, right? That's what makes a good teacher. Yeah.
I was curious as far as finances go. Sounds like you work with NASA.
Beta my existence, yes.
Yes, sounds like you work with NASA, which I understand
A lot.
is governmentally funded.
Yes.
And
Sometimes unfunded.
first thing I was wondering was, is NASA, is it affected by politics?
Do you really need me to answer that? Absolutely. So I actually, on my Twitter feed, right, it says, astronomer, planet hunter, and accidental astropolitician. So I have gotten into astropolitics, which is what I call it. I did not mean to, did not want to. I'm an introvert. I don't actually like talking to people I don't know. But nevertheless, I have become an astropolitician, I guess, because I'm good at it. I don't know. But for example, on April 9th, I'm going to go to Washington, D.C., and I'm going to lobby to make sure that the W first mission, which by the way Trump canceled, and Congress, thank God, reinstated, and try to convince them not to cancel W first and give us the money we need in order to do this thing. So, and you know, I'm reasonably good at explaining these concepts to people that maybe aren't that familiar with the science.
Yeah.
So yes. It's all politics.
Okay.
Not all politics. It does get to science, but to get to the science, you have to go to a lot of politics.
Sure. And so it sounds like you have sort of to be an evangelist and help raise public awareness.
Yeah, I don't know if I call it evangelism. You are healed. No, you have to be what I'm doing, right, technically is rocket science, but it's not really that hard. Right? I mean, I think you all can if I sit and talk to you for a half hour, you can all understand how a star shade works and blocks light, right? So no one asked me this, I'm surprised. Why does the star shade have that weird shape, right? Why isn't it just a big disk, right? Well, the reason is actually quite simple. If it was just a big disk, then what happens is when light hits the edge of the disk, it diffracts, okay? Which means it's just a wave, because light is a wave, and it interferes with the disk, and it actually focuses the light directly into the center of the disk. So you get a bright spot right in the center of the disk, exactly where you don't want it. But if you have this flower-shaped edge, then you think about it, every place where that light might hit is going to diffract the light in a different direction, away from your telescope. And that's why it's shaped. Right? You don't need to know wave optics to understand.
Yeah.
So I wouldn't say evangelist, I would say someone that can explain things at a level that other people can connect with and go back to the same
Back to the stargazing.
Space daisy.
Space daisy. What materials did you guys experiment with before you decided on whatever it was you decided?
They started off with cardboard and duct tape. And I'm not even kidding. I'm not kidding. It's actually quite funny. I walked into the lab and I'm like, cardboard, duct tape, don't let the taxpayers see you. Probably what you would use is carbon fibers to do the truss structure to keep it rigid, right? And then you would use some sort of fancy like mylar kind of thing that's very flexible and can roll up, but is very black. You don't want this thing to be, you want it to be as black as possible because you don't want, so because somewhere off over here is the sun. The sun's really bright, right? And you absolutely don't want it to be reflecting off of that and going into your telescope. So you have to make it very black, it has to be flexible, and you use techniques of origami such that when you let the star shade go, it wants to unfurl. So it was really great. There was a great moment when I visited the Star Shade lab at JPL, different one from when I said cardboard. When they had the space daisy all rolled up into this little ball, it started, remember the movie, right? And basically it wants to unroll, right? So it's being held there by these rods, right? and it's under enormous amount of pressure, right? And so if you just let go of one of those rods, the pedal will unfurl extremely quickly, right? So there's enormous potential energy locked up in this thing because it wants to unfurl. And so I'm standing there like, this far away from it. And I realize that, there are these steel rods that are holding it in. If one of those steel rods breaks, that little pedal is going to come out and I'm dead, right? And I said, should I be worried? They're like, nah, it's fine. I'm like, really? But you have to learn how to trust JPL engineers. They know what they're doing. So anyway, it's technology. It's things that we know. We've made other things before. We've never made anything quite like this, but you might not be surprised that there are large deployable structures out in the space, some of which we know about, some of which we don't, or at least we don't. Some people know about, unless you have higher clearance than I do. I do have a JPL badge, but I can't go in some buildings. And a lot of that originally comes from the defense industry and gets eventually brought into astronomy.
So who or what was the W Space Telescope named for?
The W first?
I heard
James Webb.
I just heard W.
W first stands for Wide Field Infrared Survey Telescope.
Okay.
Boring. So all NASA missions start off with a super boring name. So James Webb was called the NGST, Next Generation Space Telescope. Spitzer was called SIRBIF, the Space Infrared Telescope Facility. And then right at launch, when launch happens, they usually rename it to something for a person, usually a famous dead scientist. In the case of James Webb, there was a NASA administrator who actually really helped NASA develop.
There was one frame of national politics when I heard W, I thought of a president. That was what happened.
So there's been an infinite number of jokes about W first, but one of the things W first is going to do is actually explore dark energy. You guys are familiar with dark energy. 70% of the universe, actually 95% of the universe is made out of stuff we don't know what it is. About 25% of that is what we call dark matter, which means we don't know. And then we have dark energy, which means we really don't know what that is. Right? And dark energy has this really super bizarre property that it actually it has negative pressure. So instead of attracting things, it pushes things away, and it's causing our universe to accelerate. Really weird. Anyway, W first is going to try to study the nature of dark energy. One of the ways we parameterize dark energy is by the letter W. And if W is -1, that means it's a certain kind of dark energy called a cosmological constant, which is what Einstein came up with. So W first wants to measure W, lowercase w. So people that joke about it and don't like exoplanets, which is what I want to use it for, call it W first.
What is life like as an astronomer? You mentioned your graduate students, and I've heard hellish stories about how hard they have to work, and then if you survive that, you can make it postdocs and tenure. And are most of your grad students going to make it to tenure? Are there other tracks to go through?
There's lots of questions.
Do you have to be a good manager because you're managing
there?
all
I
this
don't work
stuff?
very hard. You have to work your ass off. I mean, I'll be that honest with you. And most of the graduate students, most people that get their PhD in astronomy will not end up as tenured professors of material research universities. There's just too few spots and too many graduate students. Fortunately, graduate students have, astronomy graduate students graduate typically with an enormous skill set that lots of companies that have a lot of money and pay their employees very well, like Google, love. Because what you're doing is you're taking data and you're analyzing it, and you're looking for patterns, right? And you're using those patterns to make models and then make predictions. Google, that's basically what Google does, period, right? That's a very simplified version of what Google does. So they love astronomy PhD students. So I always joke that if this astronomy thing doesn't work out, then I'm going to go make a lot of money and stuff like that. The real answer to your question, however, is that I do work very hard, and my friend Keith does the best of that. But for me, it's not work. For me, it's in second grade. My second grade teacher, I remember every said to me, the name of 9 planets. And from then on, it was my, that was my passion. I found it, and so now it worked for me in that way. So I spent last night between 6 o'clock at night, 10 o'clock at night, writing a white paper for the decadal survey as a group to try to convince them to give us money to do something. And that was my Friday night. But for me, it's the idea that I get to participate in in trying to answer this question. It's been around for centuries of millennia. That are we alone in the universe? Sometimes I wake up and I'm dumbfounded that I actually get to help participate in this search for life. So for me, it's an honor to do this. But yeah, it's hard. It's true of everything.
Great. Well, thank you.
Thank you.
So that pretty much concludes our program. Again,